Okay, welcome to a video doing a work solution for a current electricity question for the AQA Physics A-level. Okay, if you haven't already read the question, pause the video and read the question now. Alright, so it says here that we have, here's our circuit diagram. We've got an EMF of 12 volts, internal resistance of 1.5 ohms, there's a 2 ohm resistor and an unknown resistor R. The battery supplies a current of 4.2 amps. Show that the potential difference across the internal resistance is 6.3 volts. So we're to show that the voltage across this here is 6.3. Right? So how are we going to do that? Well, if we look at the current here is 4.2 amps. It will go in here, split up. We don't know how it will split up, but it will come back. It will be 4.2 amps here as well. So we do know that the current flowing through this resistor is 4.2 amps, and we know its resistance. So we can just use Ohm's law, V equals IR, sub the numbers in, 4.2 times 1.5, and hey presto, the answer is 6.3 volts. Next step, calculate the potential difference across the 2 ohm resistor. So essentially, this internal resistance is in series with these other two resistances. I could redraw this circuit diagram like this. 1.5. You got your 2 ohm resistor there, and you've got this unknown resistor here, right? And there's a voltage across them of 12 volts, right? And we know that the voltage across this bit is 6.3. Right, so we're basically using Kirchhoff's voltage law. The sum of the voltages across all the components in the circuit must be equal to the voltage supplied, basically. So if that's 12 volt across all of this, then across this chunk, it's going to be 6.3 plus whatever it takes to make 12. So if I do 12 minus 6.3, I get my answer of 5.7 volts. So that means there's a voltage, because these are in parallel, the voltage is going to be the same across both of them, but it's 5.7 volts across this one and 5.7 volts across this one. So it's actually probably a good idea to add the information you get as you go along to your circuit diagram. Makes it a lot easier. 5.7. Okay, so as though I've got two voltmeters there. Alright, so calculate the current in the 2 ohm resistor. So now that I've added that information now, I think it makes it a bit easier for me to spot. Oh, I've got the voltage, I know the resistance, I can just use Ohm's law again. So since V equals IR, rearrange for I equals V over R, and the voltage is 5.7. Resistance is 2, so 5.7 divided by 2 is 2.85, so 2.85 amps, and the unit's already there. So that means that the current, again, I'm going to annotate my diagram as I go along, 2.85 amps. So you can see I've got 4.2 coming in, 2.85 goes that way. Guess what the next question asks me for? What's the current through R? Again, similar to Kirchhoff's voltage law, Kirchhoff's current law is also true, which is that the sum of the currents entering into a node will be equal to the sum of the currents leaving the node. So whatever's come in has to be equal to whatever's leaving. So that, if 4.2 cars per second come down here and 2.85 go that way, then whatever's left over must be going down there. So again, a relatively straightforward calculation. 4.2 minus 2.85. And we get a current of 1.35 amps. Again, units given to us, so I don't need to worry about it. Again, I will add 1.35 amps to my diagram, so I'm keeping my diagram up to date throughout. Calculate the resistance of R. This is R. I've got the voltage across R, I've got the current through R, so it should be relatively straightforward. Again, using Ohm's law, V equals IR. Rearrange for R equals V over I. the voltage was 5.7 and I was 5.7 and I was 1.35. Okay, so that gives me, when calculated, a value of 4.2 ohms. Okay, so 4.2 ohms. Calculate the total resistance of the circuit. Right. So if this is, again, go back to annotating my diagram, 4.2 ohms, 2 ohms. So I need to sum those two resistances. So for adding resistors in parallel, it is 1 over R total will be equal to 1 over R1 plus 1 over R2 and this goes on for as many resistances in parallel as you've got. So I have got 1 over R total will be equal to 1 divided by 2, which is the first resistance here, plus 1 divided by 4.2. Okay, so if I just add the half to 1 over 4.2 and get the decimal answer, you'll get a value of, you'll get basically 1 over R total will be equal to 0.758. Okay, so to get RT, I just take the inverse of that, so or just invert both sides of the equation. So that makes RT over 1 and 1 over 0.7858, and that gets me a value of 1.35. So RT equals 1.35 ohms. Now, since it says calculate the total resistance of the circuit, it actually means include the internal resistance, which is quite easy to miss. The internal resistance was already given to us as 1.5, so I'm, for the final bit, 1.35 plus 1.5 gets me 2.85 ohms. Okay, so quite a bit of work to do for 2 marks there. Right, now, battery converts chemical energy into electrical energy, and it's dissipated in the internal resistance and the 2 external resistors. By using the appropriate data and values you've calculated, complete the following table. Calculate the rate of energy dissipation in each resistor. So this relies on you understanding that power, which is voltage, or current times voltage usually is how it's written, you can sub into this equation for voltage Ohm's law. So since V also equals IR, you can take this and sub it in for V. So you get P equals I times R, or I squared R. So if you do I squared R for each of these, so let's go back. The internal resistance has got a current flowing through it, as we did before, and I didn't put it on, but 4.2 amps. Right, so it's got a current flowing through it at 4.2 amps. It's got a resistance of 1.5. So the energy dissipated across it is going to be, it's going to be 4.2 squared, which is I squared, times 1.5. And that comes out as 26.5 watts. Units are already in the table, so I don't need to put them in. Okay, so the 2 ohm resistor, so I have to remind myself what's the current flowing through it. It's 2.85, so it's going to be 2.85 squared times 2, and when calculated this gives me a value of 6.2. The resistance that I calculated, which is 4.2 ohms, has a current of 1.35, so 1.35 is the squared, 1.35 squared. Again, I'm just applying P equals I squared R each time, times the resistance, which was 4.2, and again when calculated that gets me 7.7. Alright, so the question's been leading us up to this. Hence, show that the energy conserved in the energy is conserved in the circuit. Alright, so if we go back to the very beginning, the EMF total energy provided was 12 joules per coulomb. The current was 4.2 amps, which is coulombs per second. So again, power equals voltage times current, or current times voltage, doesn't matter which way around, multiplication order doesn't matter. So if we do 12 volts times 4.2 amps, we'll get the total energy delivered by the battery, by the cell. And that comes out as 50.4 watts. Provided by the, now is it a cell or a battery? There's two, so it's actually a battery. Battery, right? And then when you add up the amount of energy dissipated over resistances, so we're just going to add these up, 26.5 plus 16.2 plus 7.7, and when you calculate that, it comes out as 50.4, okay, watts. Okay, so that and that are the same, so therefore energy conserved. Okay, I hope you found this video useful. Thanks for watching. Please like, share and subscribe.